Well, welcome to the last, but not least, hopefully, lecture for our short course in Bayesian statistics. I have the chat open, so if you have any questions, let me know. I know we don't have any more TA sessions, so in case you have some questions about homework, maybe ask them. You can ask them now, or maybe better toward the end of the lecture. I will have time to stay for a couple of minutes after, maybe more than a couple. All right, so let me remind you first where we are. So we have defined what Bayesian inference is, which is really, in some sense, deceptively simple in the sense that it says if you have data and if you have a data generating model with some parameters, could be low dimensional, could be high dimensional vector parameters, then all your scientific conclusions or engineering conclusions or predictions should be based on this object called posterior distribution of model parameters given the data. And we know how to kind of work with that object. That typically in practice, we look at quantiles and maybe point estimates, mode, mean, median. And so the last lecture and a half we spent trying to understand how to get to this posterior distribution or to the properties of this posterior distribution using Monte Carlo and Markov chain Monte Carlo. So, I mean, I am trying kind of just to cover like really fundamental topics without going too deep into detailed and specific algorithms. But we have seen the most important algorithm in some sense. It's like that. A ring in the Lord of the Rings. It's there was one ring to rule them all, and here it's one Rosenbluth-Hastings algorithm to rule them all in some sense. That really defines a big class of algorithms, and almost anything you see in MCMC world is a specific instance of this Rosenbluth-Hastings algorithm with with some bells and whistles attached to it. But really, that's the most fundamental idea. Everything else is sort of, in some sense, are details. Okay, so today I would like us to kind of try to analyze more problems which are not quite toy problems anymore, something which can be high dimensional and or at least medium dimensional. So the first one is this beta hierarchical model. So it's a generalization of the model that we looked at last time, where we remember we started with a very simple model when we have some counts from a population. In my example I gave was number of people who experienced COVID-19, which we can tell by looking at the antibodies. And so we had this one number, one count, and we wanted to estimate probability. We put some beta prior in that probability. The posterior was beta, sorry, also beta, because that's a conjugate prior for that likelihood, and so on. And we got our answer without any MCMC or Monte Carlo. It was really analytic and simple. So now we want to extend it just a little bit. And so now we want to estimate multiple proportions. So it's not much more complicated, but a little bit enough to cause us some problems for us. We're estimating multiple proportions. And we suspect that these proportions may be similar to each other. So they're somehow related. They're not just completely independent from each other. They may be similar in value. So, for example, in this setting that we discussed, which will not be the setting of our data set that we'll analyze today during the computer lab portion, but in our setting from the first lecture, if I wanted to estimate proportion of people who experienced COVID-19 in Los Angeles and then San Diego and San Francisco, maybe I would go to Portland, Oregon, and maybe Seattle, kind of to cover all major cities on the West Coast. Maybe I would say, yeah, they should be different. They're different cities, different, age groups, different circumstances, population density is different. Lots of epidemiological kind of circumstances are different, but maybe it shouldn't be that different from each other. Like it shouldn't be as different as Los Angeles from like London or something. So like there should be some similarities between these proportions. And if I collect the data and analyze them completely independently, I'm kind of ignoring that intuition, and not just intuition, it's prior knowledge that I have. And so what we're going to do instead, we're going to collect this data. So this will be counts of, COVID-19 people who experience COVID-19 or something else across multiple locations, maybe, or people use it for, uh, on geographical scale, but also you can think about hospitals. Maybe you're counting something in each hospital and you have multiple hospitals, so you have multiple counts. And we're going to assume the same model basically as we assumed before. It will be a binomial model. Binomial, the only difference now, I'm assuming that I have these index I to indicate that I have multiple locations or multiple somehow units of observational units. And this n sub I, right? So this is the number of binomial or Bernoulli trials. It can be different across locations, right? So maybe I collected 100 samples in Los Angeles, but 150 in Seattle, and I want to account for that. I don't want to assume that I will always collect 100 because it's not unrealistic. The real data collection is much more messier than that. So we rarely can really set our sample size exactly what we want it to be. There's usually some deviations from that, even in control settings like clinical trials, because people drop out, don't show up, and so on. Okay, we assume that yi's are independent given this theta i's, and we put the following prior on theta i's. So we're going to go and say we have lots of proportions now, m proportions. Actually, that should be also m right here. And we're going to assume that they are IID, independent and identically distributed, with prior equal beta, alpha, and beta. And when you look at this, you may say, hold on a second, Volodymyr, you just wrote exactly the same model. Like, this is not interesting. You're repeating the first lecture. And this is almost true. But the big difference here will be that in the first lecture, we assume this alpha and beta, we set them. Remember, we actually set them to like something like 2 and 20, if I remember correctly, to kind of maybe reflect the prior knowledge that these proportions should have been between 5 and 20%. But here, the big difference is that with these alpha and beta will be free parameters. So alpha and beta are unknown parameters that receive their own priors. Get their own priors. They can be really anything, but I'm going to be consistent with my code that I'm going to show in a second, where I'm assuming they come from exponential distribution with some rate specific for alpha, and beta will come also from exponential distribution with some rate specific to beta. But this is quite arbitrary. And actually, in this case, the prior influence is minimal, so you could play with it prior and not much will change, turns out. So that's the big difference, because we have multiple proportions. We actually can estimate, if we assume that they come from the same distribution, and that's where the similarity comes in, right? So this is our intuition, like, okay, if they are similar, maybe they come from this beta distribution, and the beta distribution, if it has small variance, it will mean that they're very similar to each other. If it has large variance, if it's uniform between 0 and 1, they all completely kind of unrelated to each other. But we're not going to force that. We're going to estimate alpha and beta ourselves. If alpha and beta are close to 1, right? Beta 1, 1 is uniform distribution. So if they're close to 1, then we'll say, yeah, they're all over the place. But if these parameters in the posterior, alpha and beta, come out different from 1, then we can look at them and see how similar or different the thetas are. And that's the reason why we have the word hierarchical in the name. And another way of looking at this is this. Sometimes we like to describe our data generating models in statistics using graphical models, which are directed acyclic graphs, DAGs, where you kind of put each variable or each random variable in your model, including the data, which we assume the data also random realization of a random variable. And what it says basically that notice, like, if I know theta 1, it means that I can generate y1. I don't need to know anything else. So that's these DAG encodes conditional independencies basically in the model. It's a beautiful subject to graphical models. If you haven't seen this, the classic text is Stephen Lawrence's text about graphical models, but you can encode these dependency between variables this way. And so theta, this model says that given thetas, y's can be generated independently, and we know from what distribution, from binomial. And then it says that alpha and beta, they influence each theta separately, right? So alpha and beta, theta 1 comes from beta distribution with parameters alpha and beta, theta 2, and so on. So this is the way to kind of conceptualize this model, and also conceptualize why it's called hierarchical, because it's sometimes also called so let me write another name that you may see, multi-level. Sometimes people use multi-level, and that's because we have these, it's kind of arbitrary what you call level 1. Let me call it level 1 here and level 2 here. But those are kind of two layers of parameters, and given the alpha, the first layer is kind of the top one, and then given the first layer, you can generate from your model the second layer, and then the third layer is the data, and you can generate the data. So it kind of tells you how to proceed if you want to generate new data from this model. Any questions?
Maybe how realistic is the assumption that y i's are independent of each other given theta i's?
It depends on the setting. It's a good question, Valeria. In some cases, that's not sufficient, and so you want to do something else. I would say so. So here, notice what's interesting about this. It's conditional independence, and it's not full independence. So we actually don't assume anymore that yi's are completely independent from each other. So if you integrate kind of theta out and all the parameters out, y's will be dependent on each other. They in this model they are exchangeable still. So the order of the indices does not matter. So this will yield exchangeable distribution on y's, but not but they're not independent anymore. Um, if you think about our experiment, if I know the proportions of, let's say, proportion of people, true proportion of people who had COVID-19 in each of the cities, like Seattle, Los Angeles, and so on, then my sampling is done independently. So that's realistic. So if I know my true proportion, I'm sampling independently. I'm not calling Seattle and asking them any questions when I'm sampling people in Los Angeles. So in that case, it's very realistic. In some setting, it could be questionable, and you may do something else. I would say more questionable assumption is that this one is that thetas are IID and come from beta distribution, because that actually is potentially problematic. And so that's where people usually relax this model. So for example, here we assume that thetas are independent, but they're similar, but they come in there's no structure, where in reality, maybe we should assume that Los Angeles and San Diego, for example, should be much more similar because they're close to each other geographically, relatively speaking, by US standards, not by European standards. But Seattle is much further, so there will be that should be taken into account. And so instead of this simple distribution, you can actually put a Gaussian process maybe on these parameters that accounts for spatial dependencies, and it explicitly uses distance to encode how much they're dependent on each other. So that's where people usually put a lot of effort on this in this layer, not in the necessarily here, because that's usually less problematic. Okay, good question. Anything else I can clarify before we move on?
I have a question. So
Uh-huh.
after we update our distributions, will alpha and beta depend on I, or they the same for all?
Oh yeah, we assume that alpha and beta are global kind of parameters. Yes, they control all i's. So yes, there will be only one alpha, one beta, but m thetas. So we'll get all of them together.
I see.
1 second. Did I? Did I erase so much that I'm writing a lecture and then I'm erasing it. Now I'm questioning, did I erase too much? I think I did. Yeah, maybe I'll need to add something on the fly because I forgot to specify the posterior. So let me first move this a little bit. So I do want to make sure that we understand the components of the posterior distribution. So posterior distribution in this case will be density of all the thetas, right? So theta 1, theta m, alpha, beta, conditional on the vector y, right? So this is our posterior distribution. So this is all we don't know, conditional on what we do know, which is the data, which is the only thing we know. And so this will be, as always, proportional. Remember, this integral on the bottom, we don't really know in practice, but it's proportional to the likelihood. And the likelihood in this case will be product of individual binomial probabilities. So it's yi given theta I. And this is where conditional independencies come in. Notice I don't need to condition on alpha and beta or other thetas. I can drop everything except theta I. So that's my likelihood. So maybe we can specify this is my likelihood times product of density of beta distributions, and I need to condition on alpha and beta here. So this is my this is interesting. That's kind of unusual. This is prior one in some sense, but it's a hierarchical prior. It's not a full prior, right? Because I'm conditioning on alpha and beta. And then the last one is I put independently, shall we hold a second? Some probability density, alpha times density, prior density of beta. So this is my sort of, in sense, prior two. And this whole thing, really, it's a joint density of all the thetas and alpha and beta. So this is like, joint prior distribution of all the parameters. We just decompose them into two parts, the marginals for alpha and beta and the conditional of theta given alpha and beta. So now I hope it's clear that we can compute each of these terms. We cannot compute normalizing constant, but this is just a Bernoulli probability mass function product of that. This is product of beta densities. This is product of exponential densities. So everything is computable here. And so that means we can plug this into our Rosenbluth-Hastings algorithm that we discussed last time, because for that algorithm, we don't need a normalizing constant. So it doesn't matter that we don't, this symbol right here means proportional to, right? So that this does not bother us. Okay, any questions? So this is the posterior, but notice the posterior here is high dimensional. For example, in this little demo that I'm going to show, m, the number of units, will be 71, 70 or 69 or something, like 71, I think 71. So it's, we have 73 parameters, so it is not low dimensional anymore. I cannot just do some scribble some integrals on a piece of paper and actually find out what this posterior distribution is.
So we have just this generalization. Yeah, if we take m equals 1 and alpha and beta be non-random numbers, we just get the posterior density from first homework.
Exactly. Yeah, absolutely. That's right.
Yeah, thank you.
But this generalization becomes intractable analytically, basically. And that's why I kind of like it, because it's sort of the simplest way to make things suddenly intractable analytically, and you need to do something else. In this case, you do need MCMC or some other approximation. There's some others, but not many. Yeah, that's a good point. It's a strict generalization of our beta binomial model from lecture 1. If you have seen, I don't know have you seen the term random effects in before? So this could be considered a random effect model where we are assuming that some of our effect sizes are random. It's a linear modeling terminology, random effects, mixed effects modeling in classical statistics. I mean, so this is kind of analogous to that in frequency statistic. Okay, so in our example, we will actually look not at the cities, we will look at rats. Interestingly enough, it's a sort of classic example that everyone likes to use, and I also like to use it. So we will have number of rats in a rat colony under study. And Y will be number of tumor occurrences. In rat colony I. So in this setting, basically what happened is it's an experiment that scientists were running. They had these animal model rats in particular. They had multiple sort of cages or enclosures with them, and they were studying the effect of different genes on tumor occurrences, right? So they are trying to understand how, the mechanics of cancer basically using rats. And so in each colony they had they counted after some time period how many tumor occurrences they observed, but the number of rats was different because it's very messy when you work with animals. You cannot really control their numbers all the time. The scientists, when they do the experiments, it's kind of it's the whole industry. So these rats or mice are shipped to them by some companies, and sometimes they don't receive as many as they wanted to. And so anyway, there's lots of variation in these experiments. But it's basically the same idea, right? We have some count data Y, and Ni will be our kind of individual sample sizes. We'll see that in a second. Before we go into the computer lab, I just wanted to mention we will be using something called Hamiltonian Monte Carlo, and I know it came up during discussion with Thanasi and Jesselyn on Tuesday. It's a separate topic, but I just wanted to briefly mention it so at least when you see the terminology in practice. So this is right now probably the most popular approach to Bayesian in terms of computational approaches to Bayesian modeling. And so it's a particular type of Rosenbluth-Hastings algorithm coupled with some actually data augmentation. So there's some trick to that that needs to be done before you start doing Rosenbluth-Hastings. It uses Hamiltonian dynamics, interestingly, and kind of some interesting physical analogies to generate Rosenbluth-Hastings proposals. And the reason it's very popular right now because it works really well in high dimensions. So it generates the high dimensional proposals, which are really good in the sense that they are accepted quite often, so they're not wasteful. So it works well in high dimensions, especially the no U-turn sampler. It's a little modification which was important called NUTS when people abbreviate that variant of HMC. So basically what it does something very similar to what we did and what you're doing in your homework right now in homework 3, but instead of generating these small univariate proposals using uniform distribution or something else, it uses some tricky machinery to generate whole vectors. So in our case, it will generate 70 three-dimensional vectors as proposals, and then it will form this Rosenbluth-Hastings acceptance ratio exactly the same way I showed you in class on Tuesday. No, hold on a second. Was it Monday? Sorry, on Monday. And we'll accept reject using exactly the same formula that we talked about. The only difference is this. Remember, the Rosenberg-Hastings has this Q proposal density distribution that is very flexible. So it's in this case, it's using something really clever, and it implemented in many programming probabilistic programming languages. For example, Stan is a C++ based language, but it can be called, and we'll do that today. There's some APIs that you can use, can be called from R or Python and Julia as well. You're probably, since a lot of you are coming from mathematical community, you're probably familiar with Julia more than others. But Julia is a relatively new programming language, scientific programming language, designed to be as fast as C++, more or less, but as easy to read and write as Python, or R, maybe. Maybe Python is a better analogy. Pyra is another implementation in Python. Turing is a native implementation in Julia. Actually, my research group is using Turing a lot, but we're using less Stan right now. A little less Stan, but we still use Stan. And many more. So this algorithm became so popular, it's implemented everywhere, basically. Like every time you want to do an MCMC these days, it's implemented everywhere. One limitation of this algorithm, you can only work in continuous spaces. If you have a discrete parameter, for example, a change point, that's a very typical parameter. Like you have a change point, you don't know where it is, and you don't know how many change points you have in your time series, maybe, and something like that. So when you have discrete parameters, it cannot do anything because it's based on gradients. So this proposal, when it's constructed, because it's using Hamiltonian dynamics, it needs to compute gradient of your posterior distribution, or more precisely, log posterior. And that can be done only when the notion of gradient exists. And so it does not work in discrete spaces. So if you want to sample networks, if a network is your parameter, for example, it will not work. But for us, it will work, because notice, for us, all of these parameters are continuous, right? So gradients, we can take gradients of this log posterior, that's fine. I know it's very high level, so and to be honest, it will take me probably another 4 lectures to go into HMC, so that's why I cannot really go there too much. Okay, so let's as I'm switching to laptop to do computer demo here, let me know if you have any questions. I'm happy to answer them as I'm transitioning. So this code is already online. Sorry, I didn't post it. I just pushed it, I think, today in the morning. And I'm using not RStudio, but Visual Studio, because it renders for some reason mathematics better for me. But you can do it everything in RStudio as well, the same way. So yeah. Minimize this a little bit. So this is, I adapted it from some teaching materials that also we did, and I want to acknowledge Isaac Goldstein, who was a graduate student in my research group, and right now is a postdoc at Stanford. And it's mostly Isaac's doing in terms of converting my old code into this much more beautiful lab. So we need some packages. Some of them are less important than others. There's, tidyverse is the usual one for just data wrangling. Tidybase is kind of an interesting package that allows you to analyze outputs of these Bayesian machineries, MCMC samplers, in a straightforward way. RStan is actually the main library. So here, this is what I was talking about. So RStan is something we will need to learn right now a little bit. I'll introduce you to it, and then you can learn it later on your own when you need it. But that's this probabilistic programming language that allows us to write Bayesian models, but not write custom MCMC code, which is quite annoying, writing your own MCMC code every time. So this type of nice package did not exist when I was writing my dissertation in the early 2000s. There was actually a package called what was it? Winbugs, which could do something like that, but it was hard to use it for high dimensions. So I had, every time I would start a new problem, I would have to write completely new MCMC from scratch every time. And so that was quite time consuming. Now we can do it much easier, and I'll show you in a second how. And posterior is just some other auxiliary libraries. That's not important. Here also you can parallelize, sometimes when you do MCMC, if you want to run multiple chains, you can sometimes do it in parallel. Even my little laptop has 4 cores, so you can parallelize your computations, but we're not going to do it right now because who knows if it's going to, sometimes it needs more work and babysitting. So we're going to read the
Monte Carlo, Markov chain Monte Carlo, right?
Markov chain Monte Carlo, yes. Yes. Yeah, it will be MCMC, yeah. So I pushed to the GitHub, you have this, this little toy example, well, somewhat toy example, which called red data. And if you look at this red data, sorry, my console is pretty small, but I hope you can see on the bottom these numbers. They're just vectors of 2 numbers, right? And so they're ordered by the number of rats in the colony, number of tumors. So for example, colony 1 had 20 rats, but 0 tumors, like nothing happened. And that's fine. And so that happens for some number of colonies. Then for these colonies, you had 20 rats, but 1 tumor, things are random, 19 rats, 1 tumor. And then at the very end, you'll get colony 71, we had 14 rats and 4 tumors. So they're ordered not by the numbers, they're ordered by the proportion of the rats that developed tumor. Right, so this is our data set, right? 71 by 2 table. Number of successes, number of trials, different for each colony. So you can think of them as geographical locations too, if it's more convenient and so on. Right, the data set is clear, and you have it on GitHub. Actually, everyone has it on GitHub. The GitHub repo is public, so everyone can download that. Okay, so what next code does, it's all the magic is here, but the magic is based on specification of the model, which is hidden in a separate file, it turns out. You sometimes can blend them, but it's easier to have it in a separate file. So this file right here, so notice this is function stan that calls this file, which defines basically everything, except we will begin passing the data. So we're going to create a list of things that we're going to pass to this function stan. So it will happen right here. And here we'll passing the data, a number of observations, the data, the axes, the ends, and our priors. So these 0.1 and 0.1, keep note of that. That will be rates of our exponential priors. But nothing is here is clear. Like, it's not obvious why this will sample beta binomial model. It's not defined, because everything is defined in this file, separate file. And let me open it right here. It's right here. So let's walk through that. It's very explicit, and it takes time to get used to it, but it's not very long. Like, look, this is the whole line. It's 42 lines. So the whole model is specified in 42 lines. First is data. Data basically is everything you are passing to file. It's not necessarily only data, because it treats our parameters for the priors as data as well, which is not really data. It's just a constant. So basically, all the constants that you want to pass to the function, you're passing through this interface called data block. So what we're doing here, we're passing the indicator function. This says basically, do I want to sample from the posterior or only from the prior? Sometimes it's useful. We're not going to do it today, but it could be useful sometimes. Next, I'm passing the number of observations. It's an integer, and notice it's kind of written as a C, like C++ style, because it is based all on C++. But it's its own language basically. It's actually not C. It's its own probabilistic language. So it has defined everything. For loops and everything is defined inside stan, not in C++ in some sense. It's using C++ under the hood somewhere. So this is how we're passing the data, right? This is our vector of X, vector of N, number of trials, and this is our parameters for alpha. This is where we are going to pass this 0.1 the rate of our exponential prior for alpha and the rate of exponential prior for beta. Here we're going to define the parameters. This is a vector of real numbers between 0 and 1. That's going to be our thetas. And also our positive parameters alpha and beta right here. Right, so this is our definition of parameters. And this is the full model. And notice it's written almost the same way I wrote it in the lectures. It says alpha is exponential with this parameter lambda. Beta is exponential. And then you can use a for loop to say, and this sign really does mean distributed as we usually use in mathematical in the notes. So, but it's now coded. So now this Stan will understand that I'm saying it's a distributional statement, and it will understand the distributional statement. It automatically will put the right likelihood components into the posterior, and it will do automatically. It will assemble the posterior basically automatically for us. We don't have to multiply binomial probability mass functions and beta densities ourselves. It will do it for us. And here in this for loop, it says, thetas are coming from beta, and if I'm not doing priors, right? If I'm doing real Bayesian inference, then I need to specify my likelihood, which is binomial. Xi given theta I will be binomial. Again, it's the same formula basically that I wrote just 10 minutes ago in my notes. So it's very expressive language, very explicit, very easy to use if you because you're basically writing a model and you have just to know a little bit of syntaxes to make sure you use square brackets in the right places or something like that. And then this is actually, we can ignore this for now, but you can actually generate fake data from your model this way too. But for now, we can actually safely ignore this. This is the main, just 3 blocks will actually give us everything we want for the purposes of this lecture. Any questions about this? Kind of, do you see how math translates into this code roughly? Quite explicitly, actually. The only kind of, I would say, annoying block is this data block. It's not, that's something we didn't, we just wrote. It's easier to write when you write mathematics on a piece of paper, but here we have to be a little more explicit because we're passing something to the computer program. So it's very simple. No questions. I can go to back to lecture 4 code. And so I'm not gonna actually, this one is pretty simple, so let's rerun it. So what's gonna happen? Of course, I didn't do everything else. Okay. Set the seed, load the packages, load the data. And then, so notice on the bottom, if you could see it, maybe I'll, so we start the run, and we'll also specify that we want 4 chains, 4 independent MCMC chains. It's useful because if one of them did not converge, you start worrying, okay, maybe I have a complicated problem and I should be more careful. If all 4 of them go to the same place, you're more comfortable. The number of iterations, just 1,000 actually, very small number of iterations, because this HMC trick works really well. And we specified a separate seed to pass it to Stan because it uses its own seed, not our R seed. It uses its own C++ seed. And so notice it ran these 4 chains. It has some warm-up period and actual sampling period. And so and it saved everything in our posterior fit object. We can look at the trace plot. So here on the right, there's a trace plot, and it's actually probably rendered better in my pre-run. Yeah, let's look at that. It's rendered better. So notice this trace plot is plotting number of iterations. This is kind of the same plot. Remember during last lecture, we did the fuzzy caterpillar plots for Ehrenfest diffusion and for the normal model. So it's the same, except remember, there's a bit of a difficulty here. If you have one parameter or if your state space is one-dimensional in MCMC, you're just plotting your state across iterations. And that's what we did for Ehrenfest diffusion. That was number of molecules in the left box. Or for normal model, that was normal. Here I have 73 parameters. So I could plot them separately, 73 trace plots, But that's kind of, difficult to look at. And so the most important of them is when you plug in your parameters into log posterior, evaluate that, and then do the trace plot of this. That's the best diagnostics. Why is that the case? If I saw a picture where my I would be seeing kind of an increase, not like a stationarity, but increase, trend up. What it means is that my sampler is still climbing the hill. So it's not really converged. I started it in a very unlikely place, and it's trying to find the mode of the posterior, but it hasn't found it yet. So it's still going into the mode. And that usually indicates, when I look at it, it's like, okay, I need more iterations because it hasn't converged. I need to run it longer because it hasn't even found the mode yet. Here we can see that it's probably found the mode very quickly, and now it oscillates around the mode of that multivariate distribution. That's my guess, actually. I don't know what this multivariate distribution is. It's very complicated. It's not a named distribution, but looking at this trace plot makes me comfortable. All the chains, 4 chains, went to the same place. It would be worrying if one of them was on the bottom or on top, because I was like, okay, maybe there are 2 modes in my distribution, and it's a multimodal distribution, and I don't know that. So in that case, I start to worry, and I kind of do more maybe numeric work, try different samplers and so on. But in this case, everything seems to be uh, going according to plan in terms of convergence. And visualizing is just plotting. It's just you can do it any way you want. But this is one example. So this is posterior distribution of all the thetas showed as box plots. Right? So this is each. So if you kind of look sideways, that's a histogram, but it's a flattened histogram because I cannot plot 71 histograms. It's too many. So I condense them into a box plot. So these are quartiles of my posterior. These lines, these middle lines are medians, posterior medians, and so on. It's not maybe the best visualization, but it gives us something very quick to look at. And so remember how the first couple of colonies had 0 counts of tumor. That's why they have the lowest probability of tumor. But notice they are not 0. That's something that frequentist actually inference would have hard time doing, because we made an assumption that all of these colonies should be not crazy different from each other. And we're borrowing information basically from colonies who had counts, non-zero counts. We're borrowing the information from them and saying, these theta are small, but they're not 0 because these thetas cannot be too far from the thetas here, which are about 20%. And so basically we're saying if we observe zeros, well, maybe it means that the probability here was 5%, but not 0%, right? So that's the beauty of this. It's called shrinkage in Bayesian inference, when you are your parameters kind of shrinking to be closer to each other. The posteriors are shrinking. If I did this problem one at a time, right, the alternative is to do what we did in lecture 1 and just say, okay, it's a beta binomial problem for colony 1. Let's solve it. 2, and so on. If I did it separately, these thetas would be much more volatile. Oh, sorry, these box plots would be much more volatile. They'd be kind of jumping all over the place too much. They will be too noisy. But because we made an assumption, and again, it's an assumption and should be tested. You should not trust all the assumptions. Actually, that's what statisticians are the best. We are very skeptical of our models. That's what distinguishes us from applied mathematicians. We are not falling in love with our models. We're always, aware that model misspecification is always on the table, and no matter what you think. And so, but still, when we're testing this assumption, under this assumption, we made it kind of smoother in some sense. We made these thetas not to be crazy different from each other, and so that allowed us to estimate thetas even when the counts were really low, and got some meaningful maybe uncertainties around it. Hopefully, meaningful uncertainties. So that's kind of the simplest example of this Bayesian shrinkage or Bayesian hierarchical models, where you're trying to borrow information across multiple studies or units or whatever, it's geographical location and so on. We can also look at the, notice this is posterior distribution of theta. We also have posterior distribution of alpha and beta. Remember, alpha and beta, unlike in lecture 1, they're not fixed. And so remember that we said if the alpha and beta was 1, 1 uniform, that would means that thetas could be all over the place. But alpha and beta are not 1, 1. They are, more like 5 and 15 or something like that in the posterior distribution. So that it's interesting, and you can also think about what it means for us and what it means in terms of similarity of thetas, and you can study that posterior distribution of alpha and beta to kind of understand more similarities between alpha and betas. And remember, our prior was actually quite silly. Our prior was exponential 0.1. So it's definitely not this. So our posteriors are very different from prior, which is a good thing in terms of identifiability. That's what you want to look at as a Bayesian. You want to think as if your priors and posteriors are very similar to each other, that means your data did not inform you about this parameter, which could be okay, but if your prior is good. But that makes you think really hard about whether your prior information is valid, and if you have thought hard enough about your prior. In the next example, this will actually become very important. Well, I will have time for it, but not as much time as for this one. But this one is more fundamental, so I'm happy spending more time here. Any questions?
There is a warm-up part of the program and sampling part. So what do they do?
Yeah, so all of MCMC. Remember, MCMC always has tuning parameters. So in your homework and in the lab in the class, the tuning parameter was the width of the uniform random walk window, right? So we could choose it small or could it large. So these tuning parameters are always there. HMC also has them. It's using leapfrogging algorithm for solving Hamiltonian dynamics, and there's this little step size which is a tuning parameter in that algorithm. So what it's trying to do during the warm-up, it tries to find the most optimal tuning parameters. So it's basically kind of spinning its wheels, not doing anything useful for us yet, but trying to adapt to this particular data set to make a better job during the actual sampling. And the sampling, that's what we actually see in the output. It will give us only the sampling part. It will hide the warm-up and it will pretend it didn't happen. There's lots of engineering kind of tricks that are not particularly interesting, maybe sometimes mathematically, but they're important for making things work in practice. So that some of these are kind of hidden under the rug, maybe. Okay, so let me switch back to to set up another problem. Especially since it is stated in the description of the course, I would feel really bad not showing it at all, especially since it's what I do for a living. And okay. So I kind of wanted to show it's a more exotic example, but I think it's useful to see that also because it kind of shows that you can do almost anything with these models. Well, there's some limitations, but you're very flexible in terms of how you can formulate these Bayesian models. So this is like a classical SIR, susceptible infectious removed example from infectious diseases, where mathematically speaking, we're trying to model the infectious disease outbreaks using differential equations. Actually, the differential equations are limits of stochastic systems, which I don't have time to go into, but there's a stochastic version of these systems. But when population size becomes large, you can rescale things and apply diffusion limit, which gives you a stochastic differential equation. But then the asymptotic mean of that stochastic process becomes differential solutions to these differential equations that I wrote here. And this is an example solution where, just to give you intuition, if if you haven't seen it, or it's been a while since you have seen it, although during the pandemic, I think we all have seen this curves and equations even in the news. So for example, in this case, I started my system with almost all susceptible population except maybe 1 or 2 infectious individuals, which are in red curve. And then as you evolve this system, and it's a nonlinear system, so you have to solve it numerically. You cannot solve it analytically. Then the number of infections goes up, susceptibles are depleted, they go down, but also you're removed after you stop being infectious, you are removed from a population. Removed means either recovered or in unfortunate cases, maybe dead. But you're removed from the dynamics of the system. And so sometimes people like kind of to write draw progressions like this, right? So you have this progression. So each individual, if you had an individual level agent-based model, you would model each individual like this, and each individual will go from susceptible state to infectious state, and then from infectious state to recovered state. And eventually the epidemic dies down. But notice it doesn't mean that you ran out of susceptibles. It means they're low enough that the dynamics stopped, but you still have some susceptibles in the end that left. Okay, so this is just mathematical description of the model. What the data are, actually is a little annoying, as always, in some sense, from a mathematical point of view, because it's not as straightforward to think about how to fit this model to data. The typical data that you have seen also during the pandemic is the vector y, and it's a time series, where yi is number of new cases. And let me change this new to red because it is annoying. New cases in interval ti plus 1. And usually that would be just a week. But in general, I just want to put some time points. But typically cases would be reported, okay, so this is during that week, we have seen 20 cases, 50 cases, and so on. That's annoying because this is not an object that we have in these differential equations. It's hard for me to connect this y to the differential equations because I don't have this. It's called incidence data, and I don't have incidence in my SIR model. But it would be nice if I had this object, which is I'm going to call NSI. So this is number of transitions from S to I, which is called cumulative incidence, or the total number of infections up to time t. Because if I had that, then I would do the following. I would say, okay, so then let's form delta NSI I, which will be N, oops, not S, NSI Ti plus 1 minus NSI Ti. And that will give me number of new infections, right? Because if I'm subtracting total number of infections at time 5, let's say, minus total number of infections at time 4, what's left is number of new infections that happened between time 4 and 5, right? So that's the kind of actually a very important trick, which is somehow not even in infectious disease books. It's people who know what to do, but it's not very well documented, that trick. And it turns out it's very easy to add to standard classical SIR this cumulative number. Notice what's happening here. When I'm counting my prevalence, I'm saying that I'm adding new infections at this rate, which depends on the product of susceptibles and infectious. So it's called, mass action, law of mass action right here. So, and beta is my transmission rate. And I'm subtracting people who recover or recover and die maybe together, removed overall. So gamma is my recovery or removal rate, more precisely. So, but if I don't subtract gamma, I will only be tracking new infections all the time. So my I would always go up, which is not what I want, because eventually it needs to go down. But if I just keep that term, basically, that's what I'm saying. If I just keep the term and I define my derivative of this new variable as just beta s I times I of t, and I don't subtract anything, then this tracks cumulative number of infections, right? Because I'm not balancing anything out. It always will go up. The same way susceptibles will always go down, because I'm subtracting kind of people who have got infected. The same way, this cumulative number of infections will go up. And so basically, that's a little addition that you need to do to standard SIR model if you want to connect it to data, to case data, to incidence data. Because then what we can do, we can just say, okay, if I knew the true number of infections, new infections happening in the week 1 or 2, there's some proportion of them that don't get reported. So I'm gonna multiply them by some number, which is gonna be my case detection probability. And so I'm gonna assume that yi's follow a negative binomial. I have a question next, why negative binomial? We're gonna get to that in a second. And negative binomial here, I'm parameterizing in terms of mean and variance. And notice the variance is a function of the mean. It's a quadratic function of the mean. That's a nice property of negative binomial. And so we're gonna say that yi are noisy realization of some proportion of infections that we have actually observed, because not people are testing, not all people have even symptoms. And so and then the other parameters are just, so E is an over dispersion parameter of negative binomial. And mu is just the mean of negative binomial in my notation here. And sigma squared is variance. And the reason why using a negative binomial, it's convenient for count data, but more importantly, it's more flexible than, let's say, Poisson. We could assume Poisson, and some people do, but I don't advise that. The reason is because Poisson distribution is very constrained. In Poisson distribution, mean and variance must be equal, and it almost never happens in practice when you look at the data in terms of, empirical mean and variance. It's very hard to find data which are Poisson distributed. There's usually some strange things are happening, and usually the data are over dispersed. So you kind of want variance to be able to be larger than the mean, or smaller if it's under dispersed, but usually it's larger. And so our likelihood in this case is really just, if I know my ODE parameters, notice what's happening. If I know my ODE parameters, I can solve my ODE and get this number n sub si number, and just multiply these negative binomial probability mass functions, PMFs. And my posterior will be then proportional to this likelihood, product of negative binomial PMFs. And I need to specify priors, which I usually, I'll do something simple for in the code. We'll see it's you can assume some, basically all of them will be log normal for if they're positive, and for the proportion we're going to assume that logit is a normal distribution, something similar. So we have 4 parameters: transmission rate, removal rate, case detection probability, and over dispersion for the negative binomial. So relatively simple model. In practice, to be honest, I would not use it really to analyze real surveillance data. It needs to be a little more complicated, but not by much. If I add time varying parameters and I make it add some non-parametrics to it, it becomes pretty good at this point, and it can be used in practice. So it's almost ready for prime time, but not quite. I'm gonna switch just for a couple of minutes. I know I'm running a little late, but let me show you. So this is pretty much the same. Oops, I forgot that. I forgot that my notation is a little different here. Sorry about that. I forgot about this inconsistency. So this cumulative incidence, I'm calling it here C, and my data is not Y but O. So let me show you so this is the data that Isaac simulated from a stochastic model actually, but it's very, very large population. So here's these compartments, right? S compartment, as in the picture in the notes, goes down. I compartment is green, goes up and down. And then this R and C compartment. So R, the blue one, is the removed people, and this purple line is this cumulative number of infections that we're using in order to get to the new infections. Sorry, it's not very big screen. And then what we did, we subsampled these, the finite differences of this purple curve, and we got the data, which is this case data, fake data from this model. So it's a simulated data, but these cases are coming basically from this. They are coming directly from this distribution right here from this. So we have the C curve in the plot, and we use it to sample this negative binomial across multiple time points, and that's what we get. And it looks pretty realistic in terms of like an outbreak data. And so the model is the same model that we specified, again, with modulo some little variable renaming. And so these are actually something I forgot to mention or hid under the rug. There's more parameters. The initial conditions are also parameters of this model. So I did not include them in my posterior. And this is our surveillance model. And the full posterior becomes includes also the this initial number of people in the S and I compartments. I will not go, especially since I'm running out of time, but I wasn't planning to go too much into, just to give you an idea, and you have the code, you can poke around in it if you want. It's much more complicated stand code here. So because you need to define ODE system, and there's separate like functions block where you can do that. So this is where you define your ODE in Stan. So it allows you to define ODEs. And then, you have much more, your data block is more complicated because you have more parameters. This is your parameters. Instead of transmission rate, we parameterize the model in terms of R naught, which is the basic reproduction number. But small number of parameters, 1, 2, 3, 4, 5, 6. So yeah, it's 6 because not 4, as I stated, because I forgot to put initial condition in my notes. I'll correct that. This is some transformations that we need to do. And this is where you integrate your ODE. So you integrate it using, surprise, surprise, Runge-Kutta method, right? RK. So it's Runge-Kutta numerical solutions. And that's where we form incidence. Notice this line, basically, that's what I said in the notes. I want incidence is cumulative infections at time point t minus cumulative infections at time point t minus 1. And then the model is basically very simple. The model says what my cases are negative binomial, undersampled negative binomial with true incidence as a mean times rho, and over dispersion. And that's it. That's the whole model. Like, the only difficult part is carefully connect ODE so you can actually get to this object in your distributional statement. Everything else is relatively easy. And so in the end, we can, again, this is the MCMC, run MCMC. I already pre-run it, and then this is your posterior. This is the dotted lines are the true values that we used for simulation, and we pretended we didn't know them. And this is the posterior that we got, and as you can see, it's pretty close. These black intervals on the bottom, those are credible intervals of different width, 95 and 50, I think. So we didn't get them perfectly, these parameters, but we did pretty well, in part because we also specified priors carefully. So that's something I'm not showing here. And also you can do something that I want to end with is posterior predictive check. This is important when you want to check adequacy of your model. So what this plot is doing, it's basically taking your posterior parameters. Imagine you have your MCMC, you have a matrix. At each row, you have one iteration of your MCMC, and you have parameters. Then you basically, given these parameters, you solve the ODE and you produce new data, fake data. You simulate data from that iteration. And then you do it again and again and again. And that basically generates posterior predictive that you did analytically in homework 1, by the way. That's why I wanted to do this so you could do it analytically. But in this case, we're doing it numerically. So you generate posterior predictive distribution. And what we would like to see, if our model is good, our posterior predictive, we should be able to produce basically fake data that looks like real data. If we cannot do that, something is wrong with our model. It doesn't fit well, right? So if I cannot produce fake data that looks kind of like real data, I'm in trouble because it means that my data generating process is broken somehow. And so this is really good for diagnostic. It's very similar to frequencies goodness of fit type of ideas, but it's Bayesian version of the goodness of fit, basically. So we want our predictive posterior distribution basically kind of to cover the data, so the data does not look unusual. It's not in the tail of that distribution or too much in the tail. It's okay to be occasionally in the tail, but not too often. It doesn't have frequencies guaranteed. It's not a frequentist object, like in a sense, like, I don't have I cannot make p-values out of this, for example, although people sometimes do, but I don't want to go there. They're a little strange, but there is a posterior predictive p-value. Actually, when I said this, I remembered that there's a term, but it's not calibrated in a way you think it is. But in this case, because it's simulated data, we can see that our model fits well, and that's not surprising because we've simulated data from this exactly the same model. So that would be a problem if it didn't fit well. And really last 2 seconds is just want to mention a couple of words. What's next for you if you want to learn more? So those are a couple of references. So the Bayes rules one is, I used to basically guide you how to set up your system if you want to use RStan, which again, I on purpose kind of pushed RStan to the very end so that people who didn't have it installed wouldn't struggle and would be able to do the homework. But if you want to play with the code that I just showed today, you would need to install RStan using the instructions, and it should all run. And the second book is also actually by my former colleague from Seattle, Peter Hoff, who is now at Duke. This is also introduction to Bayesian statistics, but it's a little more, the first book, Bayes Rules, is very gentle, aimed at undergraduates, not necessarily even math majors. So it's very gentle introduction. Peter Hoff's is more master's level, maybe first-year master's students or advanced undergraduates, more mathematical, basically. So I think if you're coming from a math background, you probably will enjoy Peter Hoff's book a little more in terms of style. Bayesian data analysis, Gelman, Carlin, Stern, and so on. This is classic, kind of applied, but very comprehensive Bayesian text. It's kind of it's a Bible of applied Bayesian statistics. It's a good reference. It's not necessarily good to read it all because it's very thick and it has everything in it, but it's a good kind of encyclopedic reference in some sense. And statistical rethinking is a kind of a new, relatively new comer to this market of books about Bayesian statistics, but it's really well done, and it tries to kind of rethink some of the stuff that we typically do in a frequentist way to show it in a Bayesian way. And not saying that one is better than the other; they're complementary. But it's kind of interesting to an interesting take on how to kind of teach Bayesian statistics to scientists and others. So, and of course, more books, but I just kind of wanted to select some of the ones that are tried and proven in this business. Okay, well, that's it for our series of lectures. If you have any questions, I'm happy to answer them.